Welcome to OfficeHr3. So I just want to say a few things. First of all, Pearson was down all of yesterday for the homework for Chapter 4, so as you've probably seen the message, the deadline's been changed to Wednesday night, and because of that, Chapter 6 is also Wednesday night the next week. But I do want to encourage you to get going and started on as much as Chapter 6 as soon as you can, because it's quite a bit longer. The atoms chapter has kind of like two halves to it. The first half is kind of very basic stuff that you might have seen in middle school or high school or something like that. And that's talking about the structure of the atom in terms of neutrons, protons, and electrons. Now, chemistry is how the electrons behave. So we're going to be all about the electrons, including the second half of the chapter, electron configuration. But the protons determine pretty much how the electrons behave. So they're in the middle of the nucleus and they're attracting the electrons. The electrons are kind of in these orbital things on the outside, but the balance between the number of electrons and protons is important. And then the neutrons there help the protons stick together in the nucleus. And so the actual number of neutrons doesn't affect the chemistry, but it does affect the stability. So only certain isotopes are stable, other isotopes are radioactive or unstable in decay. And then in the middle of Chapter 4, you have to learn how to calculate an atomic weight. The atomic mass is the mass of one type of atom, an isotope. The atomic weight is a weighted average based on percentages and the atomic mass of that particular isotope. And so you have to learn how to calculate an average using percentages. And then stuff I've written up here is probably not familiar to anybody before this class. The text introduces the idea of the electrons in the atom kind of form a series of shells, and that's given by the quantum number n. And n is more or less, at least for the s orbital, what row in the periodic table you're in. So n starts at 1 and then goes through up to 7 in the periodic table. Then after that, there's an idea of subshell. Subshell is kind of like another quantum number, except in the subshell we actually don't write the number itself. We use a code, and so it's like the Christmas Story movie, you know, the decoder ring for Ovaltine and so on. So 0 is an S, 1 is a P, and 2 is a D. The thing about the S is it can hold 2 electrons, and so we kind of draw a box to put those 2 electrons in. P type is made of 3 boxes, so it can hold up to 2 in each box, so a total of 6. And then D can hold up to a total of 12 because there's 5 boxes. And so, basically you fill electrons into these boxes from the lowest energy one up to until you run out. And if you're putting into a set of boxes, you put 1 up in each one, and then you start pairing them downwards. And so I want to show you how this works. But the other thing, when you reach the end of the chapter, you learn that particular electron configurations are special, especially stable, and that's when you filled the S and the P. And that takes 8 electrons, 2 in here, 2, 2, and 2. It's a total of 8 electrons. And when you do that, you're always at the noble gas. Now, noble gases, the electrons don't like to do anything except stay on the noble gas atom, and that's why they don't bond with anything. Now, all this stuff about electron configuration is not used a whole lot in later chapters. It's mainly used to explain why ions in Chapter 6 have the charges they do, and that's important for understanding ionic compounds. Ionic compounds, the common name for them is salts, so, or electrolytes, and so on. So you surely have heard of those. And then this whole thing about 8 being special is also the basis for the octet rule, octet meaning 8, in covalently bonded compounds, which are what molecules are made of. And ionic compounds and covalent compounds are really completely different. So the first half of chapter 6, ionic compounds, second half, covalent compounds. So let me just illustrate. I've drawn the boxes and the order in which they appear. So the lowest box is 1s, and hydrogen has 1 electron. There you go. You put it in, and if you want to write down what the electron configuration is, you would write 1s and then a superscript 1, and it's just pronounced 1s1. All right, you don't say to the first power. These things are not powers. All right, so the rule says, okay, I've done all the up ones I can because I've filled this series of boxes. The next one goes down. All right, well, that's helium. Helium is 2 electrons. And so now we'd say 1s2 instead of 1s1, because now we have 2 electrons in the 1s. However, we've reached our limit for the 1s, and I've drawn a little line here in pink. And so every time we've filled in something that corresponds to a noble gas, we have what we call the noble gas electron configuration. And now lithium starts, you start a new row in the periodic table, because in the periodic table, the last thing is the noble gas. After the noble gas, you start a new row. All right, so if you start looking at the structure of the periodic table, the first 2 columns are actually, when you're filling in, the last electron has gone into an S-type box. Then the other side of the periodic table, which has 6 elements wide in it, it's called the P block, and the last electron you have put in was in the P shell, where the noble gas is where you filled all 6 electrons into the P shell. And so this is neon here, where you have filled up the 2P. So you keep going. All right, so 1. Okay, that's lithium. Next is beryllium. Beryllium, you put the next one here. You don't put it in here because this is higher in energy than this. So you half fill a certain set of boxes at one energy level, and then you pair them up, and then you go to the next. All right, so now 1, that would be boron, 5 electrons, carbon. All right, and so that's where this rule really starts to come into play. Nitrogen and oxygen, fluorine, neon. All right, hey, neon. Then you start a new row in the periodic table. Sodium, 1 more electron, and it's like that. All right, so after sodium is magnesium, aluminum, silicon, then phosphorus. All right, so for example, and after phosphorus comes sulfur. So let's write down what we have for sulfur. Sulfur is 1s2. There's 2 in the 2s. There's 6 in the 2p. There's 2 in the 3s box, orbital box. And then there's 4 in the 3p subshell. And then, of course, for phosphorus, that's all there is. But the way you do is you just double check everything and see that you have, should be, oh, sorry, this is sulfur, sorry. Sulfur should have 16 electrons. All right, the other thing to note is that that is a core like helium, that's a core like neon. So instead of writing all this every time, you can just take the noble gas from the previous row, just write square bracket that, and you don't have to fill all those shells again, and then just put in the valence electrons. And there's only 6 valence electrons after neon in the periodic table when you get to sulfur. And sulfur, as a matter of fact, is in group 6A, and the group number in the old A and B system tells you how many valence electrons you have. So a little bit more about the subshell. So it turns out that each layer introduces a new type of subshell or set of orbitals. So it turns out the S's look like spheres. So the 1s is a tiny little sphere, and the 2s is a larger sphere. But when you reach a new type of, a new shell, you reach a new type. So there is no such thing as 1p. There's only the type S in n equals 1. So for n equals 2, this number out front is the n quantum number. So 2, so this is shell 2. Shell 2 has 2 types of orbitals, the S and the P. Shell 3 has 3 types of orbitals, and I did not write down 3D, but has 3 types of orbitals, 3s, 3p, 3d. And when you look at shell 4, it has 4 types of orbitals, 4s, 4p, 4d, 4f, and then shell 5 would have up to g's and so on. That's way past where we're going to concern ourselves with. But every time you get a new type of subshell, you actually have more boxes too. So S-type, there's only 1 of them. P-type, there's 3 of them. D-type, there's 5. And then the F-type, there's actually 7 boxes. And that means you can put in 14 electrons. So if you actually look at the bottom of the periodic table, there's a series of elements, 14 elements in a row. And those elements are where the last electron you put in was put into one of a set of F boxes. So that's what the subshells are. And each course subshell has its own characteristic shape. So I said the S's look like spheres, the P's look like dumbbells, and the D's look like clover leaves, most of them do, and the F's look like a koosh ball. They have so many things sticking out all over the place. You're not expected to know what those look like, but you should know something, that the P has something to do with the shape and how the electrons are going around the atom. So remember, the original model was the electrons were like in a circular orbit, like the Earth around the Sun. And so these are called orbitals, but they're not circular orbits. They're not even elliptical. They're just kind of fuzzy. We call them electron clouds. So the subshell tells you the type of electron cloud that particular electron has. Here we go. All right, so this is asking about the atomic weight, and so I'm more than happy to do that. So gallium-69 has a total of 69 neutrons and protons, okay? And so when you actually weigh that particular atom, not on a balance, it's way too light for that, but you can actually determine exactly what its mass is. So the mass will be close to 69, but not exactly 69. The reason is that every time these nuclear particles come together, some of the mass gets converted to energy, all right? And so we have decided to say, okay, well, you know, you can't just simply add up the masses of the neutrons and protons and electrons, get this mass number. You actually have to measure it. And so now this number is always very close to 69, all right? And so I'm going to guess if gallium-71 is the other isotope. We're about to find out. I think it's gallium-71. So if you're not given gallium-71's percent abundance, and if there's only 2 isotopes, you know from the fact that the percentages have to add to 100, that it must be 39.9, okay? So I subtracted this from 100 to get this percent. And its mass, if I'm going to guess, it's going to be 70.962. Now, it won't be exactly right, but it's going to be darn close. All right, so notice what I did is this is 2 more neutrons, and I'm just going to guess that the atomic mass is 2 more. And that's going to be a really close guess. So how do we calculate the average? All right, now assuming these numbers are close to actual reality, the average should be the percent as a decimal number. So don't write 60.10, but it's 0.6010 times the mass, 68.962, plus the other percent times the other mass. 0.399 times 70.962. Now, if this information is all correct, the actual answer is on the periodic table as the atomic weight of gallium. All right, and so I'm thinking it's slightly less than 70, so it'll be 69 something. But other than that, let me find out. I have a periodic table just off screen here. Different book. All right, so gallium, 69.723. All right, so the actual numbers may differ. So there might be more than 2 isotopes, or the numbers might be somewhat off. But this is actually how you calculate atomic weight. Now, the other thing is, you should be able to work backwards. If you're given the periodic table, you know the average. And if you're given 1%, you can calculate the other percent. If you know one mass, then that only leaves you one unknown, the other mass. That's a kind of a more complicated, but it is doing the same problem. So the most straightforward application is knowing all the percentages, knowing all the masses, multiply them together, add them up, and you'll get the average. But we have to use percentages to calculate averages for atoms. And so if you would imagine, if I asked you to calculate the average weight of a person on planet Earth, well, by the time you're finished counting, there's probably 1 million more people. And so, how do you do that? And so it's really impossible to actually count individual atoms, add up all their individual masses, and divide by the number of atoms. So that's just not practical. Strontium with 51 neutrons? Let me see if that's, yeah, that's reasonable. Okay. So strontium is that. So I have to look in the periodic table, see what atomic number that is. That is 38. So the element symbol is basically the number of protons. Just from the periodic table, you look up strontium, see 38 for the atomic number, which is the number of protons. So that's P, the number of protons. And then the superscript is the number of neutrons plus protons. So I know that this, since there's 51 neutrons, and the superscript is both protons plus neutrons, it's whatever the number of 51 plus 38 is. Of course, that's not how you'd write it. You'd actually add the two numbers. So it's 89. So it's strontium 89. So that's how you work that one. The exam will be multiple choice. The ionic stuff will definitely be on there, and I'm thinking probably most of the covalent. And so I will let you know as the time approaches how much of the covalent part of the material will be on the exam. So the textbook has basically a section where you learn how to name the covalent compounds and write their formulas. That's pretty easy. And then this business with Lewis structures, which is not so easy. And I may just stop there. And so, for example, if you think about how can I ask a question about Lewis structures, well, you may have to draw it and then count how many things you drew. So let me just give you an example. Or I might just draw you a couple, 3 wrong ones and 1 right one, and ask you which one's the correct one. The ionic compounds, they transfer electrons because one gives and one takes. And that's okay because they're both happy. Because usually what happens is both of them reach the noble gas electron configuration, but sometimes it can't be done. So both want to take because they're both nonmetals, and that can't work out. So they have to share. And so we'll do water. So when you have a Lewis structure, first of all, you got to figure out who's attached to who. And so in water, oxygen's in the middle. Now I drew it this way for a particular reason. That's its actual shape. But oxygen has 6 valence electrons. So when you look at the periodic table, it's in column 6. So I'm going to use the Lewis dot structure. So basically with Lewis dot structure, you draw a dot on each side of an atom until you run out of electrons. Well, I got 2 more, so you just start pairing them up. So the Lewis structure for oxygen is 2 double dots and 2 single dots. Now generally speaking, that means it needs to share this electron in a bond and this electron in a bond. All right, so a dash is shared electrons. So hydrogen is in the first column periodic table, which means it has 1 outer electron. It's the only electron it has. And so here's another. So you can think of it as this hydrogen with 1 electron needs 2. This oxygen is going to share 1 electron with it, and that's this OH bond. And then this other unpaired electrons get shared with this hydrogen, so they're both sharing these 2 electrons. These are the 2 electrons being shared. So every dash in the Lewis structure is 2 electrons being shared between the 2 atoms. And there's at least 1 bond between each atom, otherwise they wouldn't be holding together. And then the last part is the double dots. The double dots don't need to be shared. Oxygen only needs to share these 2. Doesn't need to share these lone pairs. So now the octet rule says, hey, now oxygen's happy. It's got 8 electrons around it. It has these 2, it has these 2, these 2, and these 2. And actually, the best way to count these electrons is by pairs. So 2, 4, 6, 8. Who do you appreciate? Water. All right, and so all the structures are like that. And so sometimes, though, you have to draw 2 bonds, like in carbon dioxide. All right, so let me write carbon dioxide up here. But if you can't draw the Lewis structures, then you really can't master the following section, which is based on the Lewis structure. What's the shape going to be? Because water is bent. Again, that's pretty far in your future, like a week and a half or so. I just want to show you how to draw a Lewis structure. Carbon has 4, and as a matter of fact, that's why there's so many carbon compounds. It's because carbon can form bonds in lots of different ways, but it needs to have a total of 4 bonds. Oxygen, 6, and another oxygen, 6. All right, so the skeleton of carbon dioxide is carbon's in the middle. Oxygen, no, it needs 2 bonds. This is only 1. And this one needs 2 bonds too. So it turns out the best Lewis structure is going to be that. And then the 2 double dots on each oxygen atom. And now we have the correct Lewis structure for CO2. And you better count the electrons before and after when you do this. So carbon's got 4, oxygen has 6, and another oxygen has 6, so that's a total of 16. Then you count them by pairs. 2, 4, 6, 8, 10, 12, 14, 16. All right, so even though a Lewis structure on a test might have an octet around everybody, if there's the wrong number, it's the wrong answer. All right, so always count the electrons you got to put around, and then after you put them around, count them, make sure you didn't put any extra in or leave any out, because that's a bad thing. What days? Okay, well, that's a great question. Okay, so there's a reminder, sign up and schedule your exam with ProctorU at least 3 days before you actually want to take it. All right, otherwise they're going to charge you a little bit, but it's still, you don't want to mess with that. So go ahead and schedule the time now. if you know what the time is with Proctor U. And that gives you a lead time to kind of make sure you have an account and all that stuff. The other thing is, what was the question? So there's a window from Wednesday morning, the 5th, through the 10th, I believe.